In the previous lecture, we introduced the concept of free body diagram as a graphical representation of relevant forces and distances needed for writing the static equilibrium equations for a rigid body. In this lecture, we are going to examine several such rigid bodies and show how to construct a relevant free body diagram for each problem. Here, we have a car that weighs 2 kilonewtons. We assume the weight acts at the center of gravity of the car. A cable attached to the car is holding it in place. The tension force being applied to the cable is denoted by T. The car rests on a stationary track that makes a 50-degree angle with the horizontal axis. The key distances are known. We wish to draw the free body diagram for determining the magnitude of force T. We start by placing the weight of the car at its center of gravity. This is going to be a downward force of 2 kilonewtons. The car rests on the track at 2 points where the wheels are in contact with the surface of the track. The wheels we treat as rollers. Therefore, there is going to be a perpendicular reaction force at each roller support. We are going to label these forces as P and R. Since we are considering the system as a whole, no other force appears in our free body diagram. Let's establish a convenient coordinate system. Let's define the x-axis along the inclined plane like this. So, except for the 2 kilonewton force, all the forces are acting in the x or y direction. We can rewrite that force in terms of its x and y components. Here is our coordinate system. Here is the 2 kilonewton force. It makes a 40-degree angle with the x-axis. So the y component of the force becomes 1.29 kilonewton, and its x component is 1.53 kilonewtons. Here is the revised free body diagram. We are now ready to write the equilibrium equations. But before doing so, you may want to rotate the entire free body diagram 50 degrees clockwise in order to align the x-axis with the horizontal axis, if that makes it easier to write the equilibrium equations. Either free body diagram gives us these static equilibrium equations. We can easily solve them for the tension force in the cable and the reaction forces at the base of the wheels. Now consider this rod. It is pinned to a fixed surface at one end and attached to a cable at the other end. The rod carries a downward force of 85 newtons. We want to determine the tension force that develops in the cable as a result of the applied load. What does the free body diagram of the rod look like? Here, since we want to determine the internal force in the cable, we are going to cut through the cable and through the pin at A in order to isolate the rod. This exposes the internal forces at A as well as the internal force in the cable. Since there is a pin at A, we end up with two forces at the end of the rod, a force in the x direction and one in the y direction, and we label the tension force in the cable as T. Using the geometry of the system, we can easily determine the angle that the cable makes with the vertical axis. The angle is 33.69 degrees. We complete drawing the free body diagram by showing the relevant distances, like this. Now, we can formulate the static equilibrium equations needed for determining the unknown forces. In this problem, we have two kegs resting on a hand truck. Each keg has a mass of 64 kilograms. We want to determine the vertical force that one needs to apply to the handle of the truck in order to keep the assembly in the state of static equilibrium. What does the free body diagram of the system look like? First, let's calculate the weight that each keg exerts on the truck. Assuming that the weight acts at the center of gravity of the keg, we can replace each object with a vertical force, like this. Besides the unknown force P, there is one other force in play here, the reaction force at the base of the wheel. We label it R. Since we have the key distances specified along the inclined plane, let's define our coordinate system along that plane as well. Now we can rewrite each force in terms of its x and y components. P makes a 45-degree angle with the y-axis, so P times cosine of 45 gives us the y component of the force, and P times sine of 45 gives the x component of the force. We replace R with its x and y components in a similar manner. Note that the two 628 Newton forces each make a 45-degree angle with the y-axis, so we can easily determine the x and y components of the force. Replacing both forces with their x and y components, we end up with this free body diagram. Again, if it is more convenient for formulating the equilibrium equations, we can rotate the entire free body diagram like this. Here is the free body diagram where only the relevant forces and distances are shown. This is all we need in order to write the equilibrium equations. Note that we have a redundant equation. The first two equations are identical, but that is okay. We only need to use one of them, since in this problem there are only two unknown forces, P and R. Here we have a joist being held in place via a rope. Knowing the weight of the joist, we want to determine the tension force in the rope that keeps the system in static equilibrium. To draw the needed free body diagram, we cut through the rope and denote its tension force as T. Further, since the joist is in contact with the ground at two places, one being the vertical surface and one being the horizontal surface, we are going to place a horizontal force and a vertical force at A, like this. Given the length of the joist and its inclination angle, we can easily determine the relevant distances for the free body diagram. And knowing the angle that the rope makes with the horizontal axis, we can write T in terms of its x and y components. Having this free body diagram, we can easily write the equilibrium equations for determining the three unknown forces. We will examine more free body diagram problems in the next lecture. See if you can draw the correct free body diagram for the following problems.